in this video, as part of instance-based learning, let us study Introduction to Instance-based Learning and K-nearest neighbor algorithm. In contrast to learning methods that construct a general explicit description of the target function when training examples are provided, instance-based learning methods simply store the training examples. Understand the difference? In the previous algorithms, we were trying to make a hypothesis. But here, when we fed, in the previous examples, when we fed the training examples, we tried to form hypothesis. But here, the training examples are just going to be stored. Now, generalization beyond these examples is postponed until a new instance must be classified. So much processing is going to take place when we feed the instances. That is not the case with the previous algorithms. That is Bayesian learning algorithm, that was not the case. Each time a new query instance is encountered, its relationship to the previously stored examples is examined in order to assign a target function value for the new instance. Instance-based learning includes nearest neighbor and locally weighted regression methods that assume instances can be represented as points in a Euclidean space. It also includes case-based reasoning methods that use more complex symbolic representations for instances. Instance-based methods are sometimes referred to as lazy learning methods because they delay the processing until a new instance must be classified. So as I told you before, when we feed the examples, the processing is not going to take place, they are just going to be stored. Processing is going to take place when we feed new instances and ask for classifications, when we feed new instances. One disadvantage of instance-based approaches is that the cost of classifying new instances can be high. Every time we are feeding instances, some processing has to take place. That is not the case with the Bayesian learning algorithms. This is due to the fact that nearly all computation takes place at classification time rather than when the training examples are first encountered. Therefore, techniques for efficiently indexing training examples are a significant practical issue. We need to index the training examples when we want to classify new instances. And each time we are going to feed instances for the purpose of classifications, the processing will take place. So it's a kind of costly thing. A second disadvantage to many instance-based approaches, especially nearest neighbor approaches, is that they typically consider all attributes of the instances when attempting to retrieve similar training examples from memory. Let's see one instance-based algorithm, K-nearest neighbor algorithm. The most basic instance-based method is the K-nearest neighbor algorithm. This algorithm assumes all instances correspond to points in the n-dimensional space, that is r to the power n. The nearest neighbors of an instance are defined in terms of standard Euclidean distance. More precisely, let an arbitrary instance x be described by the feature vector a1 of x, a2 of x, and so on, an of x. So these are the attributes a1, a2, and so on up to an. These are the attributes, and with respect to x instance, we are writing it as a1 of x, a2 of x, and so on, an of x. Where a or of x denotes the value of rth attribute of instance x. The distance between two instances, then the distance between two instances xi and xj is given by d xi comma xj is equal to root of sigma r is equal to 1 to n a r of xi minus a r of xj the whole squared. And this expression is similar to the two-dimensional expression, which is x1 minus x2 the whole squared plus y1 minus y2 the whole squared. So this is an n-dimensional space. So we will be having r number of terms here. From r to r is equal to 1 to n. In nearest neighbor algorithm, the target function may be either discrete valued or real valued. Now let's first consider learning discrete valued target functions of the form f is defined as r to the power n input goes to capital V, where capital V is the finite set v1, v2, and so on, es. This is the classification set. The input instances are n-dimensional space instances. The function is r to the power n to are mapped to a capital V. Now we state this algorithm. See, we will divide this into training algorithm and classification algorithm. As we discussed before, the training algorithm is a very simple one. For each training example, x comma f of x, add the example to the list training underscore examples. That's all. Just putting it to the memory. Now, the processing comes here. Classification algorithm. Given a query instance xq to be classified, let x1, x2, and so on, xk denote the k instances from training underscore examples that are nearest to the query point xq. So the algorithm will return or it will assign argmax v is an element of capital V, sigma I is equal to 1 to k, delta of v comma f of xi is assigned to f cap of xq. So this is what is going to be assigned as classification to the query point xq. And we want the classification for xq. The classification is, it is notated as f cap x of q. And what is that value we find from this? Argmax v is an element of capital V, sigma I is equal to 1 to k, delta of v comma f of xi. Now what is this delta of v comma? This is k nearest neighbors. What is this delta function? delta of a comma b is equal to 1 if a is equal to b. In this case, if b is equal to f of xi, and delta of a comma b is equal to 0 otherwise. Now that was for discrete valued classifications. Now let's go for continuous valued classifications or target functions. The k nearest neighbor algorithm is easily adapted to approximating continuous valued target functions. To accomplish this, we have the algorithm calculate the mean value of the k nearest training examples rather than calculate their most common value. More precisely, to approximate a real valued target function, f is defined as r to the power n to mapped to capital V. We replace the final line of the discrete algorithm by the line sigma I is equal to 1 to k f of xi by k is assigned to f cap of xq, where again xq is the query point and the required classification is called f cap of xq. This gets this particular value. We take k nearest neighbors and we find its average. We sum all these things and divide by k. And this is called k nearest neighbor algorithm for real valued or continuous valued target functions. I hope the introduction to instance-based algorithms and k nearest neighbor algorithm is clear to you. If you like it, please give a like for this. Thank you.